Good morning, everyone. This is Maury Galbraith at the Western Interstate Energy Board. I want to thank you for joining this morning's webinar. The Western Interstate Energy Board has been working with the Stanford Precourt Institute for Energy on a very exciting project. The project is titled the Western Interconnection Data Analytics Project. We have been working with 3 graduate students at Stanford University in further analyzing some of the continuous emissions monitoring data for the Western Interconnection. And we have a really exciting presentation for you all this morning. I have muted all of the phone lines so that we can conduct a large webinar. At the end of the webinar, we will have time for questions and feedback on the project, so I will unmute lines at the end. In the meantime, if you have questions, you can submit them using the chat box. So again, I think we have a really exciting presentation for you this morning, and I'm going to turn things over to our 3 students, Pierre, Austin, and Ben. Guys, take it away.
Hey, thanks. This is Ben Lim speaking. I was an intern with WIEB last summer, and today I'm joined by my colleagues Pierre and Austin. And so in addition to thanking Diane and Maury for this opportunity, before I get started, I want to thank Dave Chasson at SLAC and Professor Sally Benson, the co-director of the Precourt Institute for Energy, because they both have been an incredible resource for our project. So today's presentation will generally talk about the Western Interconnection Data Analytics Project. Then we're going to jump into 3 areas of analysis that we've been really excited about. First will be a plant level analysis tool using Google Earth, which I'm going to walk you guys through. And then Pierre is going to take us through our unit level analysis dashboard, and Austin will show us a new way to look at thermal generation within a state. And I want to note here that we're going to pause for questions between each of these sections, so anyone can ask about the tools if they're looking for more information. So just click the raise hand button or submit your question to the chat box. A little bit of background. The Western Interconnection Data Analytics Project, or WIDAP for short, it seeks to provide meaningful insights and better information to policymakers and stakeholders. And currently we're building tools to help interested parties better understand the changes in generation as well as policy in the West. A bit of background on our data. The majority of our data comes from the EPA's continuous emissions monitoring systems, as Maury noted. This is a program that required fossil fuel-fired electric generating units to record data pertaining to consumption, emissions, generation, etc. for every hour of the year. And there are nearly 100 coal units and over 500 natural gas units in our data set. And that totals to over 75 million observations. Data actually exists for the entire United States back to the 80s, but we focus on the last 15 years and the Western Interconnection because the data is much more complete starting in 2001 and due to our geographic location. The 2017 data is not yet completely available, but when it is, we'll add it to our database this summer. Last summer, Max and I started this project when we were interns with WIEB by compiling this data, and we discovered some really interesting things about how coal power plants are now operating in the West. And I just want to share with you this map we created, and it gives a broad overview of what those changes were. So each black dot on these maps represents a coal-fired power plant. And on the left, we depict 2001, and on the right, 2016. The size of each dot represents the amount of electricity generated at the plant, and the darkness increases with the amount of time each plant was operating in a baseload pattern. And for clarification, a baseload pattern means that the plant was consistently operating at or near its maximum capacity. And if you're interested, we can see that in 2001 we have large dark circles, and in 2016 we have smaller lighter circles. But if you're interested in hearing more about the work and how we came to these results, please follow the link on this slide to view that webinar from last summer. And I also want to note that these slides will be available shortly after the talk. So now the background's out of the way, this brings us to our first of our three tools, the plant level analysis tool, or what I call the Western Interconnection Globe. After this, we'll get into unit level tools and lastly the state level analysis. But we see this globe that we've developed as an entry point to our other analysis tools, and it gives us a place to display our state level analysis as well as a jumping off point to ask more questions about the individual units in a power plant. What we're looking at right now is a screenshot of our Western Interconnection Globe built on Google Earth. Each pin on the map represents a fossil fuel fired power plant. The blue pins are gas plants and the black pins are coal plants. And I'm going to switch over to a live demonstration and I'll explain as I go. So this is the globe. And as I said earlier, we see the globe as an entry point to our other analysis tools. On the left, we have a list of states, which contains information we've developed with our third tool. And it brings up what we call a ternary plot, and Austin's going to talk about this in detail shortly. But I want to turn our attention back to the map. So for example, let's look at WIDAP coal plant in Wyoming. This is an old coal plant owned by PacifiCorp. And when we click on one of these pins, two plots come up. And that's emissions intensity over time and emissions intensity plotted against plant output. What we can see here is that the plant saw a drastic decrease in its SOx and NOx emissions intensity in 2011. And if we wanted to learn more about those changes exactly within each unit of this plant, we could flip over to our unit level dashboard, which Pierre is going to walk us through. But before that, I want to pause for any questions. If you have a question, please raise your hand or submit it to the chat box. And if not, Pierre, please take it away.
All right. So welcome to our dashboard. So as Ben mentioned, here we're trying to build a unit level analysis tool. What we have developed is a set of visualizations that the user can generate and interact with within a couple of clicks that we believe provide interesting insights on both operations and emissions for individual units. So as you can probably see, our tool has been developed within the Jupyter environment in Python. We've tried to make it as streamlined as possible, so all the user will have to do is select the first cell and click the Run button. A list of the plants will come up, and we can then choose the plants of interest. We will use the Comanche plant as an example for this presentation, and we can then click the Load Dashboard button. What happens here is that the data is pulled from our AWS server. This is the lengthiest part in the process. It takes about 50 seconds usually for the data to import it. There we go, 12 seconds. Now all the visualizations, as mentioned, are generated. We have a total of 4, some of them for operations, some of them for emissions, and some of them to correlate both. So our first visualization here is our monthly box plot of gross generation that gives good insights on operations. 2 information are provided here. One of them is the median value, which is represented by the green dots at the middle of each box plot, each box plot representing 1 month of operation. And the second information we have here is the variance and the range of values, the generation text over the month in question. So this is represented in the range covered by the whiskers, as they are called, and how wide they are. So months that are have small whiskers like this one are very consistent over their durations, and periods with very wide whiskers mean that there's a lot more variance over operation. Our second visualization tool is a time series of emissions. So this tool is to understand what is happening to emissions only. 2 important things to note about this plot is that we have normalized the data to make it more readable, so that we have similar ranges for all 3 emissions. If we had not done that, we would have much greater value for CO2 emissions when compared to SO2 and NOx. And the second important note is that we are using smoothing on this plot to make it more readable. What we are doing is a rolling mean of the values, because on one end, if we reduce the smoothing to the lowest value, the plot becomes much harder to read, and if we increase it too much, we might lose some of the information. So as you can see, I've just demonstrated the interactivity I was talking about. Each plot has a set of widgets, as they're called, to interact with. Here, the date range, the smoothing factor, and then which emissions to plot. One important thing to note is that the date range is synchronized between all of our visualizations, so that when comparing them, the date is consistent. Now moving on to our third visualizations, which is the first one that allows to compare emissions and operation and analyze them together. This provides a scatter plot of emissions in CO2 and SO2 when compared to capacity factor, which is a metric of operation. When the capacity factor is of 1, the unit is operating at its maximum value, and when it's at 0, it is offline. So what we see here is how the emission intensity evolves with capacity factor. We expect the minimum non-value to occur at maximum operation. This is what we see here generally. One quick note, we can change the y-axis scaling to make sure everything is showing. So for example, on that plot on the right, zooming out allows us to see both years. And so what we've built here is that each color represents a year within the range we have selected, so that we can see evolution through time. And the user can increase the number of years showing by simply moving the slider for more granularity on the data analysis. Now moving on to the fourth and final set of visualizations, which are the histograms. We've built a set of histograms to show the different modes of operations our plants take. We believe the value of the histograms is at its greatest when compared with the other visualizations we have built before, as we will demonstrate to a greater degree in our case studies that Austin will talk about later. But by default, we have efficiency, capacity factor, and CO2 equivalent intensity showing. We can observe different modes. So for example, looking at efficiency, we can see that we have a number of values at 0, which could be spinning reserve, and then we have 2 different modes of operation, one at full efficiency and one value for lowered operations. And another interesting note is that we have 2 different modes for CO2, and if we want to understand where they come from, we can reduce the time range of what is showing. And so this might take a while because this can take a while to load, but what we will see shortly is that we will only have 1 mode remaining, and this correlates to the upgrade we can see on the emissions plot we've seen earlier. But I won't there we go, now we have 1 mode. I won't get into more details on this because Austin will talk about case studies later. But before we move on to those, does anyone have any questions about this tool? Does anyone wants me to interact a little bit more with those plots, wants to see more?
If you have questions, you can submit them in the chat box, or you could also select *7 on your phone to unmute your phone and ask your question to Pierre.
All right.
Seeing no questions, I'd continue, guys.
All right. I think we will move on to the case studies with Austin that will provide us with specific examples and an explanation of what we observe when correlating it with the history of the different units and plants.
All right, everyone, thank you for being here with us today. We're really excited to tell you some stories about what you can actually get out of this dashboard that we've just shown you. So here we're looking at that same first visualization, the monthly box plot of generation for Intermountain Unit 1. So now, again, remember, it's not the whole plant anymore, it's just one of the units. And Intermountain is a coal plant in Delta, Utah. It's owned by Intermountain Power Agency, and if we look at this graph, a couple interesting things pop out to us. So you can see that from 2001 all the way until about 2009, 2010, the whiskers on the box plots are very short. What does that mean? It means that the variance observed in that month, or the spread of different generation values that the plant has taken, is very small. It's really condensed at the top line there, near full capacity factor. And that's the other thing is that the green dots representing the median generation value are right there near the top as well, indicating that this plant during that time range was operating in a base load capacity with low variance. Then if you look forward from 2009, you see those whiskers start to extend and get longer and longer and draw down towards the bottom of the plot. And that's indicating higher variance and that the plant has moved to a flexible generation regime. Now that is in line with some of Ben's findings that he discussed earlier. Again, you can reference his webinar for more information on that. So in looking at some of the drivers, what's actually causing this change in operations, one of the primary things that stands out is that natural gas has come down in price to a great degree and led to a preference for electric generation using natural gas instead of coal. A few other interesting things to note on this plot. First, if you look at 2003, you can see that those green median generation lines form a nice even line, and then it hops up by about 70, 80 megawatt hours, and that is because of an update to Unit 1 that actually expanded its capacity. Another interesting thing to note is that if you look at the end of 2011 here, you can see a gap in the generation when there's no data, and that indicates that the plant was off. And that, as it turns out, was actually because Unit 1 failed on at the very end of 2011, and then was offline for about 4 months in 2012. All right, here we're looking at the second visualization, which is monthly rolling average for emissions. And we're going to examine Jim Bridger Unit 1. So Jim Bridger is a coal plant in Point of Rocks, Wyoming. It is owned and operated by PacifiCorp. And turning our attention to the graph, we can see a couple interesting things as well from this visualization. So the 3 lines here represent CO2, SO2, and NOx. And if you follow from 2001 forward to about 2010, then you see that SO2 and NOx are consistently above 1.0. Remember that the emissions are normalized to the mean value over the whole time period. So that means we just divided each gas by its average value over the whole time period so that everything would show up on a 1.0 scale. So CO2 is slightly higher than 1 in that time, but SO2 and NOx are significantly higher. Then if we arrive to 2010, we notice that all of the gases drop to 0 for a time, and then when they reappear, CO2 is at a consistent, maybe slightly lower level, and it has greater variability. It's essentially more wiggly than it was before 2010. And the other gases have actually decreased drastically. So what actually happened here? In 2010, the plant went offline for a few months and installed emissions controls. And so those emissions controls, consisting of wet scrubbers and electrostatic precipitators, decreased the SO2 and NOx emissions very drastically, and they've remained low ever since. One other thing to note here is that CO2 cannot easily be captured and isn't captured at any scale in any plant in the West. So far there's really only pilot projects for carbon capture and storage. So if CO2 is present, that indicates that fuel is being burned and the plant is on. So when CO2 goes away, that's a guarantee that the plant is not operating. All right, now we're looking at the third visualization, which is emissions intensity compared against the capacity factor of the plant. Again, the capacity factor is what the plant is generating out of what the plant can actually generate. So it's generation over its nameplate capacity. We're going to look at Boardman Coal Plant. So Boardman is interesting because it is the only coal plant left in Oregon, and it is the source of most of Oregon's stationary SO2 emissions. Boardman was constructed in 1975 just 2 years before the Clean Air Act amendments required stricter emissions controls, and so it actually didn't have those when it was first constructed. So if we again turn our attention to the graph, we can analyze the data and see on the top chart the CO2 intensity, and on the bottom chart the SO2 intensity. So looking at the CO2 intensity, we can see that the CO2 has maybe on average decreased a little bit, but the really interesting thing here is that if you look at 2001, represented by the blue dots, you see a very dense, tight cluster of points near the top of the capacity factor. And if you look at 2017, the orange points, then you see a greater spread. So there's more capacity factors at which the plant is operating, and more points spread down into lower capacity factors.
Sorry, Mari, my phone.
If we turn our attention to the bottom graph, the SO2 intensity, we can see a couple interesting things here. So in 2001, again represented by the blue dots, there is a greater range of SO2 intensity for a given capacity factor. So that's on the y-axis, the vertical axis, there's a less tight band of SO2 emissions. And then when we come to 2017, again in the orange dots, that band really contracts and is lower than any of the points in 2001. Note that it contracts along the vertical axis, but really expands on the x-axis for the same reason I discussed above, that we're seeing coal plants kind of change their operations and operate at lower capacity factors now than they used to. So to tell the story of this plant a little bit better, we've noted a drastic decrease in NOx intensity, and that actually happened in 2011. If you were to select more years on the dashboard, you'd be able to see the exact year in which the NOx really decreased. And the SO2 intensity really dropped in 2013 and 14. So as I mentioned, the plant wasn't subjected to strict emissions controls until much, much later. And as a result, when Portland General Electric had to make a decision about whether or not, how long they wanted to operate the plant for, they had to weigh either spending $500 million on emissions controls that would allow it to operate until 2040, or installing significant emissions controls that still came at a steep cost, but not as steep, and would allow the plant to close a little bit earlier. So PGE decided to close the plant by 2020 and spent $45 million on mercury and NOx controls. All right, last we're going to look at a histogram of efficiency. So this is for Coyote Springs, Unit 1, and Coyote Springs is a gas plant in Boardman, Oregon. It has a capacity of 230 megawatts, and it's also operated by Portland General Electric. So look at the histogram on the upper right-hand side. You'll see efficiency on the x-axis and frequency on the y-axis. So just as a brief refresher, a histogram describes how frequently a given value occurs in a data set. So we really see two peaks here. We see one just above 30% or 0.3, and then we see another one centered just around 0.5 or 50%. And that, when we first looked at this, we were actually pretty puzzled. We weren't sure what to attribute this bimodal distribution of efficiency to. But when we reviewed the monthly box plot of generation, we were able to determine what we thought had happened. So now looking at the monthly box plot, you can see that around 2013, there was a drop-off in production representing a turbine rotor crack, and then when the plant came back online, it returned at 246 megawatts of capacity. So it's up about 16 megawatts but it's also being operated after 2013 at much higher levels, so close to 250 megawatts on the y-axis. And so because of that, it was producing a higher efficiency. So this smaller peak of efficiency around 0.5, 50% efficiency, represents these years after 2013, excuse me. And the lower efficiency points represent the earlier years. One last thing I'll talk about that I find really interesting is that you can see that this plant is operated seasonally. So it has this sinusoidal or up and down consistent periodic behavior that is represented through the data. So if we look at just say 2008 here, we see that right before the start of 2008, the plant starts increasing. So these are the winter months now when it's operating at high capacity, and then early spring it starts decreasing, and it looks like it was actually off for a month or two there in late spring, early summer, and that periodic pattern repeats, as I mentioned. So now we're going to enter the final tool, our third tool for analysis. This is a state level analysis, and these are what we call ternary plots. Two things to note about these plots. First is that these plots only represent in-state generation. They do not represent imports or exports, so we don't have information on where the electricity is actually being used, but we do know where it's being generated. The second thing to note is that we do not have renewable generation data. That is not included in these plots. However, we are looking for partners to help us find renewable generation data and access that and expand our analysis. And I think we can really come up with some meaningful results if that was made available. So if you have any data of that sort, please get in touch with us. We'd be happy to collaborate. All right, so this is on the right, the WIDAP ternary plot. We have these for each year and each state in the Western Interconnection. And when we look at the three corners, those describe the three metrics that we're visualizing here. So the top is the coal fraction of thermal generation. Importantly, remember that this is just thermal generation, so it's only really coal and gas electricity generation. On the bottom left is annual variance, normalized by the mean generation value. So that's a fancy way of saying we made sure that the variance for different states were comparable by dividing them by their average generation. And then on the bottom right, we see ramping severity. So this is a measure of how steep the average daily ramp is. So we put a little duck down there to kind of trigger in your mind the image of the California duck curve. There are many ways you can have a steep ramp. They don't have to look like a duck curve characteristic of California, but ramping severity, again, is just that measure of steep rise or fall in electric generation. So a couple other things to note. On the left is a legend for the different states. So you can find every character in this plot represents a different state. This plot is actually for the year 2016, and it includes one for every state. So we can kind of get a picture of how each state is operating its electricity generation fleet relative to the others. On the right here, we see a color bar, and the color bar represents carbon dioxide intensity. So while everything else on this plot is relative, I'll get into that in more detail in just a minute, the carbon dioxide intensity is actually an absolute number. So you can read off the color of, let's take this top point here, which is Montana, and we can say its carbon dioxide intensity is around 950, and those are going to be units of kilograms per megawatt hour. So As I mentioned, everything on the plot is relative. So if you look at, let's say this line right here, around 60%, it's 0.6 on the Cole fraction of thermal generation scale. However, it's very important to note that that 0.6 does not correspond to 60% of coal generation and 40% of gas generation. It is instead relative to the other two metrics. So it's really just saying, it's giving a relative position that describes whether the grid is dominated by coal fraction of thermal generation or by some other metric, by annual variance or by ramping severity. So again, these points may have higher or lower coal fraction of thermal generation, and many of the ones in this territory are actually still almost entirely coal generation, even though they look like they're appearing at around 0.6. Last thing to say on this graph, just note that being in a corner means you're 100% dominated by that metric. So a good example is down here on the bottom right, California. California is dominated by ramping severity because I'm sure as many of you are familiar with, there is a characteristic duck curve pattern that creates a high steepness to the curve. Also, it only has one very, very tiny coal plant, and so it's pretty much on a full gas thermal generation basis, which brings it to the bottom line there. All right, so let's look at an example of one of these ternary plots for a state for all of the years of data. So from 2001 to 2016. And when we look at Arizona, one other thing, sorry, I have to explain first. The smallest hexagon means 2001. The largest hexagon means 2016. So as the hexagon increases in size, you're marching forward through time. So what happens as we go forward through time? If we follow this trajectory, the hexagon is increasing in size, it's decreasing its color intensity, so it's getting less carbon intense, and it's shifting its position downward from coal fraction of thermal generation and right from annual variance, and it's coming closer and closer to this corner of ramping severity. So if we actually dig into the data a little bit more, and again, I'll just mention that this number, 37%, and a couple of the other facts I pulled out are from my own personal analysis. You would not be able to just read that directly off of the graph. But if we dig in a little bit more, we can find out that coal fraction of thermal generation has actually decreased 37% since 2001. Arizona is increasingly dominated by severe ramps. Not only is it dominated by severe ramps, but the variance has actually been decreasing since 2001. And then, as I mentioned, the carbon dioxide intensity of the electric generation has decreased, but we can quantitatively say from this graph, at least to within a few orders of accuracy, that what the percent reduction in CO2 intensity was. So if we look at this color here, saying this hexagon represents 2016, you can see it's probably around 630, and then it started out at the very top of the scale, so around 780, and that corresponds to about a 20% carbon intensity reduction. One last thing that's interesting to note is that if you really analyze this graph, you can see that in 2008, the carbon dioxide intensity was almost as low as 2016. So that corresponds with the economic downturn, and so not as a function of fuel switching, but as a function of a number of confounding factors. The carbon dioxide intensity was actually lower in was lowest in 2016, but similarly low in 2008. So let's look at another example. So Utah is also characteristic of the same pattern, where the earlier years are both more carbon intense and more and more dominated by coal fractional thermal generation and annual variance. And then as we step forward through time, we get closer and closer to the ramping severity section. So again, digging into the numbers a little bit more, coal fraction in Utah in 2001 was nearly 100%, and it's decreased since then to about 77%. Utah has been increasingly dominated by severe ramps, just like Arizona. Just like Arizona as well, the variance has been cut in half since 2001, and from over that same time range, the carbon intensity actually dropped by almost 25% in a mostly continuous decrease. So in thinking about why Arizona and Utah are shifting to the bottom right of the ternary plot, it's interesting to think about what are the drivers of that trend. So there could be a number of factors, but two that occur to us are one, serving load in California that's increasingly, if you recall, that is located directly in this bottom right-hand corner. Both these states serve load to California, and then that has an impact on the actual generation profiles within their state. And then second is that the generation mix and the load shapes within the states may be changing. We would need to do additional analysis to confirm that. But those are just two ways to think about, to kind of draw a story around what we're seeing here. So I'll stop there. Again, if anyone has any question, feel free to raise your hand or type something into the chat box, or press *7 to unmute yourself and fire away a question. Thank you.
So let's hold questions just a little bit longer, and because we do have some questions in the chat box, but we'll get to those in just a second. So why don't we proceed?
Okay.
So this is Diane Grunick. Can you all hear me, hopefully?
Yeah.
I am at Stanford University now and coordinating this project with the students and our researchers and faculty, and I wanted to just acknowledge the incredible support from WIEB and Maury Galbraith that Stanford established an internship program 3 years ago, and we brought WIEB into that program 2 years ago. And what you're seeing today is an outgrowth from that initial research that Ben did with his colleague Max. Max is now getting his doctorate at MIT. But this is an example, we hope, of the types of useful research that can be done by pairing some of our academic institutions throughout the West, certainly not just Stanford, with our energy organizations. So this has been an overview of where we are now. It's been a year-long collaboration. It will be continuing. Just to briefly note what you see on your screen, that there was the webinar from last summer that Ben noted that he and Max gave. It is available. We've got the link here, and it is on WIEB's website. And as Maury noted at the beginning, this webinar will also be posted, and slides from both of the webinars will be available as well. Then what you have seen today, the project that we call WIDAP, we have at Stanford the Precourt Institute for Energy and a specific initiative within it called Bits and Watts, which is Stanford's major research on the development of the 21st century grid. And in the website for Bits and Watts are various research projects, and we will be over this summer posting posting this webinar on that location, as well as some of the papers that we have been developing. There's another aspect to this project we did not present today, which is we have been researching the policy development in each of the states in the Western Interconnection over the same 15-year period that the students talked about today, so that we can start to see where there are at least correlations on the policy side and specifically the renewable side. Then you heard today the three tools that we call the globe, the dashboard, and our ternary plots. We are very, very much seeking stakeholder input this summer. This really is the first time of demonstrating to a larger audience the drafts of these tools. We are totally open to suggestions about changing them, any corrections that should be made, and then they will be publicly available through the Stanford website, and then presumably a linkage through the WIEB website as well. But that really does mean that people can go in at the level that we've shown by units, by plants, by states, and start to get a very granular understanding of what has been happening in the Western Interconnection in a very transparent manner. And then finally, as the students noted, we are constrained right now that our database is SEMS, which is the fossil fire database with coal and gas plants. But we all know to get a really good overview, we should be adding in our non-thermal power plants. And so we've certainly identified some sources, but we are very interested if there are individual states that may want to work with us, if there are organizations, anything that will help us on having generation data beyond just the fossil fire available, we very much welcome. So with that, Maury, I think we hand it back to you.
So thank you, Diane. I want to really express my thanks to Diane and Ben and Austin and Pierre. They have done some really excellent work here, and this collaboration has been wonderful. There's been a lot of important insights shared with policymakers and regulators in the West. We now do have time for some question and answer.